And then we're going to get into what we do with those random variables, so how to transform them, how to combine them. We're going to talk about different types of random variables, binomial and geometric. So that's going to be kind of where we're building towards eventually throughout this second half of the unit here. So the first thing, when we define a random variable, it's kind of just a more official way of defining a random phenomenon. So we talked about random phenomena in the first half of the unit. We said it's a situation where we know what can happen, we just don't know what will happen. And so with a random variable, we're actually going to define the different outcomes that are possible with our random phenomenon, as well as the probabilities associated with each outcome. And so the first part of this is kind of a review of some of the things we talked about in that first half of the unit. So we talked about probability models, creating probability distributions, and that's exactly what we're going to do with these random variables. So we're going to define the random variable using a capital letter. So X is a very common choice for a random variable, but you can use any letter, much like when we define our events for our probabilities. You can match the letter to the specific situation that we're dealing with. But every problem has to have the random variable being defined. So whether they define it in the problem or you define it in your answer, you need to know exactly what the random variable is representing. So that's going to be the capital letter. And then the lowercase equivalent will be the actual value that that variable takes on. So based on the notation, you know kind of what they're looking for in the question. Do we want you to define the variable? Do I want you to talk about a specific value? So capital letter versus lowercase there. Once we define our random variables, the next part of this is creating our probability distributions. And this is the review part. We did these back in the first half of the unit. So when we create a probability distribution, we list the possible outcomes. And then for each specific outcome, we assign a probability. So in the example that we're looking at there, if we consider tossing a fair coin 3 times, so we flip the coin 3 times and we record the results. The random variable that we want to investigate, X in this case, is the number of heads that come up in those 3 flips. So when I start to build my probability distribution, we look at the possible outcomes. So that's the X equals 0, X equals 1, X equals 2, X equals 3. So I could get 0 heads, 1 head, 2 heads, 3 heads. But then when I think about the sample space in question, those events are not all equally likely to occur. Getting 0 heads means I get 3 tails. There's only one possible way for me to obtain that, and that's all 3 tails. But getting a single head can happen 3 different ways. That head can show up on the first flip, second flip, or a third flip. Getting 2 heads means getting a single tail. That tail could happen first, second, or third as well. So there's 3 different options there. And then my final outcome would be 3 heads, only one possible outcome there. So when I build that probability distribution, then I have to calculate those probabilities according to that sample space. So the probability that I get 0 heads would be 1 out of 8. The probability that I get 1 head would be 3 out of 8, and so on. When we build our probability distributions, how do we verify that that's a legitimate probability distribution? What are the 2 conditions or the 2 properties that need to be met? All the probabilities have to add up to 1, right? The total sample space has to add up to 1. And all of my probabilities need to be what? Well, between 0 and 1, right? So all of the probabilities have to be between 0 and 1. So when they ask about a legitimate probability distribution for a given random variable, those are the two conditions we check. Do all the probabilities add up to 1, and are they all between 0 and 1? With these random variables then, there's lots of different things we can do. So one thing we can calculate or work with as far as the random variable is concerned is calculating probabilities. Now when we're dealing with these random variables, it's important to know what the notation is asking us. So when we look at this question here, what does that notation, p of x less than or equal to 2, what does that mean in the context of this problem? What are they asking us to do here? So as we discussed in the first half of the unit, notation is extremely important. Every time we calculate anything, we need the notation that goes along with it, so we know specifically what it is we're looking at. So when we use this notation with these random variables, what does that notation mean? Yeah, the probability that the number of heads we get is less than or equal to 2. So knowing what the question's asking, knowing what the notation stands for is going to be important. So interpreting our values, interpreting our calculations. And then when we get to actually calculating, so now that we know what they're asking us to do, if I actually want to calculate the probability that the number of heads I obtain is less than or equal to 2, what would I do? So how would I calculate that probability using that distribution? All right, one possibility is use my complement rule, right? The only thing I don't want to have happen is that I get 3 heads. So I could take my total sample space of 1 minus the 1 in 8 chance that I get 3 heads, and I get a probability of 7 out of 8. The other way I could attack it is doing what? Add up the ones that I do want. So I can use that general addition rule. Okay? So I could take the 1/8 for the 0 plus the 3/8 for 1 plus the 3/8 for 2. Either way, I get the same result. That complement rule, though, is always one that you want to kind of keep in mind. A lot of times it makes the process a little bit simpler, especially if that's a large sample space with lots of different outcomes. Rather than adding up a whole bunch of different values, we just subtract out the pieces that we don't want. Might be a little bit quicker. Okay? So then, as we're dealing with these discrete variables then, after we calculate the probability there, if I then change it to this, so I changed the notation slightly. Now what's happening? So what's changing from this scenario compared to the last one? This time I don't want to include 2 heads. So if I'm going to go strictly less than 2, that means I want 0 or 1. And so when I calculate that probability, I can take the 1/8 for 0 plus the 3/8 for 1. So I get a 4 out of 8 chance, or 1/2, 50-50. So the less than or equal to, greater than or equal to, when you're looking at those in a discrete random variable, it makes a huge difference, whether we include or don't include that endpoint. So be aware of that, okay? So calculating probabilities is going to be one thing, using that general addition rule, using the complement rule. The other thing, and probably more importantly, when we deal with these probability distributions, is calculating what we call an expected value. So when we look at this probability distribution, one of the things we can do with these probability distributions, besides calculating those basic probabilities, is we can look at the distribution as a whole. We can graph the results. So in the homework today, you're going to have a couple of problems where you're going to graph your probability distribution. So you're going to create a probability distribution for the given scenario, and then you're going to graph it. When we graph it, we're just creating kind of a modified histogram. So the x-axis is going to be the values that our variable takes on. So we're just listing out the possible outcomes. And then the y-axis will be scaled according to the different probabilities associated with those outcomes. Now we can use these distributions to describe shape, center, and spread. So shape, going all the way back to unit 1, could be symmetric or it could be skewed. Skewed left or skewed right, depending on which side the tail extends out on. Center and spread, mean and standard deviation. Now looking at the graph here, if I wanted to know, if I did this coin toss multiple times, so I flip 3 coins, record the results, do it again, record the results, and I keep doing that over and over and over again. When we talk about expected value, we're talking about the mean of the distribution. So expected value and mean are the same thing. You're going to see those terms used interchangeably. On my answer keys, you're going to see me use notation interchangeably, so we're going to talk about that here in a second. So they're asking you to calculate the same thing. Now what the graph tells us here is that if I were to perform this trial or this event over and over and over again, how many heads should I expect on average? So what does the graph tell me? Where's the center of the graph? It's not a trick question. It's perfectly symmetric. Where's the center of the graph? I need a specific value. 1.5. So the exact middle of my graph, the mean of my distribution would be 1.5, meaning if I were to do this over and over again, I flip 3 coins and record the results, over and over, on average, I should expect 1.5 heads to show up. Okay? Now, this particular graph turned out to be perfectly symmetric, so finding the center is pretty easy. Some of the probability distributions that we're going to run into, though, aren't going to be perfectly symmetric. They might be skewed one direction or another, and so finding the center can be a little bit tricky trying to use the graph. So the other option we have is using a formula to calculate that expected value, to calculate the mean. So when we calculate the mean for a discrete random variable, or we calculate the expected value, again, those terms are interchangeable. We've got 2 different sets of notation that we can utilize. There's the Greek letter version, so mu of x, or mu of y, or whatever variable they happen to be using. Or e of x. And again, you're going to see me use those kind of interchangeably throughout the answer keys. So I'm calculating mean. I'm calculating the average value. And so when we think about calculating averages in general, normally we would take all the values, add them all together, and then divide by the total number of outcomes. Now that would work if every outcome is equally likely. But in this particular scenario, not every outcome was equally likely. So when I calculate the average, I need to adjust the average formula based on the weight of each value. So the 0 was less likely to occur than the 1, so the 1 has more weight associated with it. And so what's going to happen is when we calculate these averages, when we calculate these means, we're going to take each value, each outcome for my random variable, multiply it by its associated probability, there's the weight, and then add up all the results. So for our coin toss example, if I wanted to calculate the mean or the expected number of heads in many trials, I would take each value, so 0 times the probability of 1 out of 8, plus 1 times 3 out of 8, plus 2 times 3 out of 8, and then plus 3 times 1 out of 8. So I take every single outcome and multiply it by its associated probability. When I multiply and add those terms together, we get the same value that we concluded from the graph. So the mean of our distribution, the expected value, the expected number of heads in a situation like this would be 1.5. When we interpret the mean, okay, understand that 1.5 doesn't make sense for a specific occurrence of this random phenomenon. If I flip 3 coins one time, I can't get 1.5 heads. So what we need to understand is when we calculate this mean, when we calculate this expected value, we're saying if we did it over and over and over again, in the long run, this law of large numbers, it says on average, we would expect to see 1.5 heads. So when you interpret the mean, you need to make sure you include the phrasing that hints at we do this multiple times over many trials. This is the value we expect on average. As far as the formula is concerned, you don't have to have this memorized. This is in the formula packet that you're going to get, but you do need to know how and when to use it. So given a discrete variable, when they ask you for mean or they ask you for the expected value, you're applying this formula here. So as soon as we start talking about expected value, as soon as we start talking about means, anytime I talk about a measure of center, I also need to accompany it with a measure of spread. So if we're going to calculate the mean for our distribution, we need to pair it with our standard deviation. Now, when we calculate standard deviation here, it's very similar to how we did it back in Unit 1. We're looking for the distance from each value to the mean. So just like we did with standard deviation, we start by calculating the variance. Now, in the Unit 1 version of standard deviation, everything was equally likely, everything was equally weighted. So we just took all the deviations, squared them, added them up, divided by the degrees of freedom. This time, though, the outcomes are not equally likely. Different values carry different weight. So in the formula, and again, if we look at the notation here, so for variance, we have that lowercase sigma squared, or we just use VAR for variance of the variable. We use the function notation. Again, you'll see those notations used interchangeably. But we're going to start by taking each value minus the mean. We're going to take that difference and square it. And then we're going to multiply those deviations by the probability of each outcome. So now that's where we're going to add the weight to each value. So that formula is going to calculate our variance. Now, variance in Unit 1 was just kind of a stepping stone to standard deviation. It was we calculate this, we take the square root, we get standard deviation. For right now, it's kind of the same idea. We're going to use it as a stepping stone. We find the variance. Whatever value we get, we take the square root, we get our standard deviation. But variance is going to play a much larger role in this random variable topic than it was earlier. So there's going to be some times where we come back to this idea of variance and its importance with these random variables. So we need to know how to calculate it. Eventually we'll need to know how to use it to combine random variables and other things that we're going to be dealing with. When you do this calculation, so if we were going to do this for our example with the coin toss, I can calculate variance and then square root, or I can calculate square root directly. So if I want to go straight to square root, if I want to go straight to standard deviation, all I got to do is throw a big square root over my entire calculation. I tend to prefer this method because what happens more often than not is if kids calculate variance first and then rely on converting that to standard deviation, they forget to do the square root part. So they get going too quickly, they find the value, and they stop too early. So I would always do it this way where we just attack it directly. And so for our coin toss, that means we would take our first value of 0 minus the mean we calculated, 1.5. We would square that difference and then multiply by the associated probability. Then I would go to my next value, which was 1 minus the mean squared times the probability. And then I would continue that process for each and every outcome. Then I would take the values, I'd plug them all in my calculator, so you can plug that all in at once, so square root, make sure to get the parentheses in the right spot, and you calculate your standard deviation. Now, in Unit 1, when we calculated standard deviation, we did it by hand a couple of times, but then we typically used the calculator. We used that 1var stats. That's not going to be an option for us this time. 1var stats is great for calculating standard deviation when outcomes are equally likely. But that's not the case here. There's no weighted standard deviation formula in the calculator. So these problems, we have to know the formula. We have to be able to calculate by hand. Okay? So knowing what that formula looks like, being able to apply it. Again, the variance formula will be given to you on the formula packet. So then you need to know how to convert that to standard deviation simply by taking the square root. But this is the formula you will get. You don't have to memorize it. You just need to know how to apply it and then take the square root to get that standard deviation. Okay. So last thing here, just another example. So we kind of drive home these main ideas here. So if we look at a probability distribution for a baby's APGAR score. So when a baby's born, they run the baby through a series of tests, and they rate the baby based on the responses to those tests. So a higher number means a healthier baby. So our random variable x is going to be the APGAR score for a randomly selected newborn. So again, we always have to define exactly what it is we're looking at. So then based on empirical data, so after many, many births, and compiling all the APGAR scores, they've come up with this probability distribution. If I wanted to verify that it's legitimate, I would quickly add up all the probabilities, make sure they go to 1. We can see that every probability is between 0 and 1, so we know we have a legitimate probability distribution to begin with. When we go to calculate the mean, so what is the mean APGAR score for a randomly selected baby? We take each value, multiply it by its associated probability, and add it all together. So in this case, we can see that comes out to 8.128. And then with that mean, we also want to interpret it. What does that mean in context? So in context, it says this is the average APGAR score for many randomly chosen babies. So this is the average value we get if we were to select many babies and measure their score. So then once we have that mean value, we can then calculate our standard deviation. So using our formula, we take every value minus the mean, square the difference, multiply by the associated probability, and then add them all together. So we get a variance in this case of about 2.066. We then take the square root of that to get our standard deviation. And then when we interpret standard deviation, it is exactly the same as what we did in Unit 1. So it's calculated slightly differently, but its interpretation is exactly the same. So when I interpret standard deviation, we say a randomly selected baby's APGAR score will typically differ from the mean by about 1.4. So again, when we interpret that standard deviation, it's that typical difference or distance from the mean. So on the homework today,